quiz is back.
Yeah.
By and large, you all did exceptionally well, so keep it up. Congratulations. A couple of notes. Those of you who tried to identify a macula densa on figure 2 did not get credit for that because it's just not shown. This cartoon does not show the macula densa, so I didn't give you credit for that one. But many of you had extra options, so you got the full credit no matter, even though you made that mistake. There are other. Yeah, the answer key I think is posted on Moodle now, or will be after class if it's not already there. So, and let me know if you have any questions. But by and large, the class you all did really well. You all have a hard copy of the problem set that is due on Sunday. Some of these problems you can start to work with now. So, for example, question 1 is something you can solve now. Question 2 is a clearance and GFR and filtered load and excreted load problem. So questions 2A through O are all questions that you can start to work with now because you know how to do clearance. Questions 3, 4, and 5 probably you can start to do those after class today. So I think a Sunday deadline for that is still pretty reasonable. The problem set is on Moodle, so if you prefer to do it electronically, you can download, the PDF of that on Moodle. Let's see. Remember that when you're doing the problems in the problem set, the goal, you'll be, in some cases, you'll just be doing arithmetic. You'll be finding the right equation and solving the equation. But I chose the values to try to illustrate a concept. And so when you get to the answer, you should think about what does that answer mean conceptually? Not just did I get the right number and do I have the right units? But what is it telling me about GFR or filtration or reabsorption or what? Okay, that's the goal of the problem set, not to get you to practice doing addition, subtraction, multiplication, inclusion. Okay, so today we're going to finish up glomerular filtration, talk about how it's controlled, which is important, and then we're going to turn our attention away from the glomerulus to the renal tubules and the capillaries that surround them, and start to talk about the molecular mechanisms for reabsorption. And we'll focus on sodium first, and then glucose, and that'll probably be it for today. And then on Thursday, we'll focus on bicarbonate and potassium, and those are probably going to be the only ions we talk about, solutes that we talk about. Even though calcium reabsorption is super important, and phosphate reabsorption is very important, but the principles will have been illustrated with sodium, glucose, potassium, and bicarbonate. Okay, so glomerular filtration, the rate of glomerular filtration, GFR, is controlled. Not surprisingly, it's regulated by things in your body. So let's do the first one that is relatively easy. The sympathetic nervous system innervates the smooth muscle cells and the juxtaglomerular cells of the afferent arteriole, and the sympathetic nervous system, especially by its innervation of smooth muscle, controls the diameter, the constriction or dilation of the afferent arteriole, which you know, theoretically, can influence the glomerular filtration rate. So, for example, dilation of the afferent arteriole, bringing more pressure into the glomerular capillaries, would increase the rate of filtration, increasing GFR. Constriction of the afferent arteriole would reduce the pressure in the glomerular capillaries and reduce GFR. So it comes as no surprise that the sympathetic nervous system controls glomerular filtration. And so here is the mechanism. The neurotransmitter is norepinephrine, just like it is with the rest of the sympathetic nervous system. The receptor is an alpha adrenergic receptor, which you'll remember, I think, from the cardiovascular section, is a GQ coupled receptor. Having just said GQ, I think I am now allowed to ask you a GQ question on an exam about, tell me the story of GQ. Why does activation of a GQ coupled alpha adrenergic receptor on afferent arteriolar smooth muscle lead to constriction of the afferent arterioles? I've collapsed it into one set of characters, increase in calcium. Where? In the cytoplasm of this smooth muscle. But you should be able to flesh out that story. Do you have any questions about how activation of an alpha adrenergic receptor leads to an increase in cytosolic calcium concentration, and how that leads to constriction? Go back to the cardiovascular section of the class, look it up, and the story is there. It's the same story. Constriction of afferent arterioles, just as we just said, decreases GFR. So when you are stressed, physiologically stressed, your body says, okay, I don't need, right now I need to survive this stress, I need to keep my blood pressure up, I need to keep my blood volume up, I need to send my blood to, I don't need to send my blood to the kidneys, I need to send my blood to the brain and to muscles and to the liver. Let's constrict the afferent arterioles. And so that's what happens. Questions about that? That's pretty easy, straightforward, but it does already introduce some of the concepts that we're talking about. Okay, the next one is complicated. You can see with all this text. You know I don't like text, slides. But in this case, the story is complicated enough that I wanted to have it in a text, and it's not in your book, and so it's in your PowerPoint deck. So there is such a thing called tubuloglomerular feedback. Some of these words are great. Tubuloglomerular feedback. So, I mean, and the word is exactly what you would think that it is. The tubules feed back information to the glomerulus and control glomerular filtration. So there's two forms of tubuloglomerular feedback, one of which is if there happens to be high flow in the distal tubule. Let's start with that. A lot of fluid, a lot of urinary fluid flowing through the distal tubule. That's the starting point. And so the idea is if there's a lot of fluid thrown through the distal tubule, there's feedback to try to limit that. It's negative feedback. It's a homeostatic reflex to try, okay, we got a lot of fluid, let's constrict GFR to try to limit the amount of fluid that's coming in at the front end, at the glomerulus, right? So lots of fluid near the output feeds back to try to limit the amount of fluid being filtered because it's sensing, okay, maybe there's too much fluid flow, right? So it's a high flow situation, higher than normal, higher than expected, higher than homeostatically desired. And so what that is what the macula densa, remember the macula densa is a specialization of cells in the distal tubule that makes contact with the juxtaglomerular cells and the afferent arteriole. Let's just go back to the cartoon. The macula densa of the distal tubule makes contact with the juxtaglomerular cells and the cells of the afferent arteriole to control arteriolar diameter and to control GFR. So this is, we're no longer looking at this input, we're looking at this feedback. So what's being delivered is, what's being sensed is sodium and chloride. So if there is a high flow, of fluid in the distal tubule, there's a high delivery of sodium and chloride, because those are the main ions in urine. You might think it's urea, but it's not. It's sodium and sodium and chloride. So sodium and chloride are being delivered to the distal tubule. The macula densa senses sodium and chloride, but let's just say sodium, which is an increase in osmolarity. The macula densa detects an increase in osmolarity in the distal tubule. So water flows. This should be a down arrow, because increased fluid flow would be a decreased osmolarity. Let's just fix that right now. Okay, so I've changed high flow, decreased osmolarity, increased water flow into the macula densa cytosol by osmosis. That causes a swelling of the macula densa cells. And it causes them to release a paracrine signal. Remember from cell physiology the difference between endocrine and paracrine? What's the difference between endocrine and paracrine? Distance, okay, so endocrine is a long distance signaling, and paracrine is a short distance, sort of diffusion-based signaling event. So ATP is released from the macula densa cells. So let's just go back to the cartoon. ATP is released into this very constricted space. Low flow, osmotic flow, swelling, high flow of a dilute fluid, osmotically dilute, water flows down its concentration gradient from a dilute fluid to a more concentrated fluid in the cytosol. Release of ATP into this constricted space is a paracrine event. The ATP is turned into adenosine, and adenosine is a ligand for a type of receptor, A1 receptors. Does anyone know what an ecto-ATPase is? Let's unpack this word. What's an ATPase?
An enzyme.
An enzyme that cuts ATP. Ecto just means it's outside of cells. So there are ATPases outside of cells. And so it cuts the ATP, it cuts the ADP, AMP, and to adenosine. Cuts off all the phosphates from ATP to adenosine. So it goes from triphosphate to diphosphate to monophosphate all the way to adenosine. Adenosine is the ligand for this adenosine receptor. And that activates a G-coupled receptor that leads to a decrease in cyclic AMP and an increase in calcium, constriction of the afferent arteriole, just like we saw above, and a decrease in GFR. So this is tubuloglomerular feedback. We started with high flow, so we're going to reduce GFR. I'm going to roll up the screen and cross out. So I wanted to give you the gory details, but let's cross out what I don't want you to memorize. I do want you to know the story, but I don't care that you memorize all the gory details. So, high flow, we need that. You don't really need to know this, this, and this, okay? The point is, high delivery of a dilute fluid to the macula densa triggers the release of ATP from the macula densa. That's the key thing. Morgan.
Maybe I'm just really confused by the language, but I'm really confused. So you're saying dilute fluid, but it says high delivery of filtered sodium and chloride, which makes it seem like it's concentrated?
It's
I'm
a high, so it's dilute, but it's a lot of fluid. So let's just say high delivery of fluid.
So then, just for understanding, can you then clarify the flow? I guess I'm confused when you say flow.
Increased
Is that just
flow
water
of
flow?
water.
Water flow?
This is all water flow.
Okay.
Increased flow of water into the cytosol. This is really just swelling of the cytosol. So this, every year this gets me and students confused. Swelling of the macula densa cells. Stretching of the cells. Oh, so this is now swelling. I'm sorry. Like I said, every year. Swelling leads to ATP release. So it's actually not GQ, but it's a different type of G protein coupled receptor that I haven't focused on in this class. It's called GIGO, and we don't need to, I don't want to get you involved in that story. If you know the GS story and you know the GQ story, and you know that this is coupled to an increase in calcium, you know enough.
So you just wanted to say activation of GIG leads to this?
Okay? Activation of a G, so that the adenosine receptor is a GPCR. Okay, yes?
On the slide sheet, it says sodium flow into macula instead of the flow.
Yeah, so, I mean, basically what you should do is just cross out that line, because that's not what I'm going to test you on. I'm going to test you on knowing this story without the lines that have been crossed out here. Okay? Are we clear? I'm trying to simplify the story that delivery of fluid, osmotic effects, release of ATP. Fluid, osmosis, release of ATP, cleaving of ATP to adenosine, activation of a GPCR that causes an increase in calcium, constriction, decreased GFR. There's the story. Those are the important details. I know it seems like excessive detail, but tubular feedback is important, and this is the molecular mechanism. Other questions? Before I start erasing. Okay, so predictably, if this is tubuloglomerular feedback for low flow, now we're gonna, for high flow, that's, previously it was for that. this was tubuloglomerular feedback for high flow. Predictably, the next step is tubuloglomerular feedback for low flow. If the macula densa detects low flow, then what happens? Well, the trigger is probably the release of a paracrine signal, prostaglandins, but it's not absolutely sure. This question mark isn't that I don't know, although I don't know. The research is still determining what this signal is. Prostaglandins is a key component, or a key hypothesis. But something is released from the macula densa cells that cause, that something is unknown, but prostaglandins seems to be it. So I would not ask you to memorize prostaglandin, because I could be wrong. 5 years from now, they could say, it's not prostaglandin, it's something else. But what is known is that the juxtaglomerular cells release renin. Okay? So the point is, low flow, probable prostaglandin release here causes the juxtaglomerular cells, these blue and purple things here, to release renin. Okay, that is key. Renin release from juxtaglomerular cells. Okay, now we have to tell the story of renin. Some of you who have had AMP1 already know the story of renin because this is part of endocrinology. But we have to tell it again because now we're talking about the endocrinology of the kidney. So we're focusing on the kidney, but so this is where the class, the way the class is split up into endocrine and kidney sort of doesn't work for us. This is endocrinology, but it's endocrinology related to renal function, so it's legit. So renin is the first step in what's called the RAA axis, the renin-angiotensin-aldosterone axis. Renin is a hormone. It's released into the bloodstream, but it's also an enzyme. So it's an enzymatic hormone. It cuts another precursor hormone called angiotensinogen. Angiotensinogen came from the liver. We'll talk about the liver when we talk about the liver in the next section of the class. You'll hear angiotensinogen again. Angiotensinogen is the precursor to a hormone called angiotensin. Angiotensin 1, in this case, there's more than one angiotensins. So angiotensinogen is a peptide precursor, and renin is a hormone enzyme that cuts angiotensinogen to angiotensin. Angiotensin 1. Angiotensin 1. Then there's another enzyme called angiotensin converting enzyme, ACE, angiotensin converting enzyme, ACE, which cuts angiotensin 1 to angiotensin 2. Angiotensin 2 is the functional hormone. So we've gone from renin, starting this proteolytic cutting to make angiotensin, specifically angiotensin 2. Angiotensin 2 activates GQ on almost all smooth muscles. Calcium is the story here, right? GQ. Constriction of systemic arterioles, right? Remember, if we constrict systemic arterioles, we increase resistance. You know, I'm going all the way back to the beginning of the semester. Remember, mean arterial pressure is approximately equal to cardiac output times systemic vascular resistance. That equation should ring a bell, even if you couldn't pull it up out of your brains. If we increase systemic vascular resistance, we increase blood pressure. So this is confusing. Not only is it complicated, it's confusing, because an increase in blood pressure by itself would increase GFR. Right? If all we had was an increase in blood pressure, then there would be more pressure in the glomeruli, and that would increase GFR. True. But constriction of both the afferent and efferent arterioles, remember they are arterioles that have vascular smooth muscle as well, constriction of the afferent and efferent arterioles, dramatic constriction of both of those, leads to a decrease in GFR. Because if we constrict both the afferent and the efferent arteriole, we get very little blood flow into the glomeruli, low flow, low filtration, low GFR. So this is feedback because we started with low flow and we're going to decrease low flow. Low flow is almost always associated with dehydration. So the idea here is, if we're dehydrated, then we want to decrease GFR. Because we don't want to filter the fluids that we're trying to conserve. Low flow is almost always associated with dehydration. The response to dehydration in the kidney, one of the responses to dehydration in the kidney is, let's not filter the fluid in order to not lose it in urine. Okay? So that's another form of tubuloglomerular feedback. This one is due to the renin, angiotensin, aldosterone. We haven't talked about aldosterone yet. We will when we get to next week when we talk about the loop of Henle. Meanwhile, did you have a question?
So then the high flow would just be when you
Yeah, high flow would be overhydration, and we want to decrease, right? High flow would be too much water. Well, high flow high flow is not necessarily because of excess water. High flow is due to excess glomerular filtration. And so this is simple negative feedback. Too much glomerular filtration, let's constrict the afferent arteriole and decrease GFR. Low flow, why would we have high flow? Excessive dilation of the afferent arteriole, inadequate fluid reabsorption, so the tubules are not doing their job, so we're not, so the fluid that should be reabsorbed by the tubules is not, so we're getting high flow at the output end near the distal tubule. So those are two possibilities for that could cause high flow. You know, it's complicated, but it's important. Morgan?
So, just to clarify, angiotensin 1 is cut to angiotensin 2, and it activates the angiotensin 1 receptors, but...
No, angiotensin 1 is a peptide that is cut by ACE
Right.
to form angiotensin 2.
Right.
Angiotensin 2 activates the receptor.
But why is it angiotensin 1 receptor?
Oh, it's the name of the receptor is the AT1 receptor because, so this is yeah. This is not the receptor for angiotensin 1. This is the first angiotensin receptor that was discovered, so they call it the AT1 receptor.
But it's for angiotensin 2.
The ligand for the
I got
AT1
it.
receptor is angiotensin 2.
Okay.
How many ways can we trip you up? Is that clear?
Yeah.
I'm laughing and you're not. It's always a bad sign. And we're going to skip atrial natriuretic peptide. Let's just leave this one aside. There are other hormones that do this too. I put it in pale writing to just indicate it's there. I'm happy to answer questions about it, but I'm not going to test you on it, and I'm not going to expect you to know it. Okay, questions about tubuloglomerular feedback? Because what I'd like to do now is turn our attention to reabsorption. We've been focusing on filtration for quite a few days now. Now we're going to focus on reabsorption by the peritubular capillaries, well, by the proximal tubule, the loop of Henle, the distal tubule. Those are the tubular components we're focusing on. Proximal, loop, distal, and the peritubular capillaries and the vasorecta capillaries that surround those tubules. Because what we want to do is we've filtered out all our goodies. Now we want to reabsorb water and glucose and sodium from the tubular fluid into the blood to go back to the body. That's the goal here now. We don't want to lose. Remember, we have filtered 100 mils per minute of water, for example. We do not want to urinate 100 mils per minute. We want to reabsorb 99% of that water. Reabsorb from tubular fluid back into the blood. So, right, here's the cartoon of the nephrons that you are expert on. You showed me your expertise on the quiz, even though I tripped you up with the fact that the quiz cartoon did not have a macula densa, but obviously nephrons do. So what we're going to do is we're going to start with sodium. And we're going to start in the proximal tubule. Okay, so that's where we're going. We're telling the story of sodium reabsorption, and we're going to walk through the tubules. So, tubules. And we will work with this more on Thursday in lab. So, here is a cartoon, a generic cartoon of a tubule in cross-section. Right? So this is a tube coming out of the board, and we're cutting it in cross-section. What are these things in this cartoon? They're cells, epithelial cells. So this is an epithelium. We haven't talked about an epithelium yet in this course. We've talked about muscle cells and endothelial cells and other cells, but we haven't talked about epithelial cells. Now they become critically important. So this is a whole new world now that we're starting to work with, epithelium. And we'll need that for kidney now, and we'll need it for the digestive tract as well, because that's an epithelium as well. An epithelium is a layer of cells that surrounds a tube. In the kidney, it's surrounding a tubule. In the digestive tract, it's surrounding the intestines. In an epithelium, there are really two important membranes. There is the apical membrane that makes the contact between the tubular fluid and the cell. So the apical membrane, so these are all apical membranes of these cells in cartoon. That's an important word to know, apical. The other cell membrane of an epithelial cell is the basolateral membrane. Basolateral. Lateral-baso. Basolateral. Okay? The basolateral membranes have junctions that can be leaky or tight. So these are, in some parts of the tubule, these are very tight. In others, they are leaky. Tight being impermeable to water, but also to sodium. So we won't focus too much on the junctions. But we need to know apical and basolateral. So, for example, so here is the way the kidney. This is a histological section through part of the kidney. This is the way the cells actually look. So here is a lumen. Here is a cell. Here's a cell. Here's a cell. All these nuclei are telling you that there's a cell here. Something like that. So there's a lumen surrounded by an epithelium with apical and basolateral membranes around it. We'll be working with some histology in lab on Thursday. So let's not get too bogged down into what this looks like, because that's what we're going to be doing together in lab. Let's focus on the cartoon. But the point is the cartoon is a reasonable, facsimile of what is actually there. So now, what do you suppose all these blobs are with arrows? Transporters. And we're going to go through this. So we're going to go through some, but not all, of the molecular mechanisms for solute transport through the epithelium. I want to introduce two more words. So here is let me introduce two more words down here. There can be reabsorption like this, which we would call transcellular. Through the cells, through the epithelial cells, through the apical membrane and through the basolateral membrane. Transcellular is going through the epithelial cells. There can also be reabsorption around the cells, and frankly, most in the capillary. In the capillary, most of the reabsorption goes around the endothelial cells, and this is called paracellular. Transport around the cells, through the cells, around the cells. The point is, material, solutes, is transported from the tubular lumen through the epithelial layer, either transcellularly or paracellularly, and then is picked up mostly paracellularly into the capillaries that are surrounding it. So here's a cartoon of a tubule surrounded by the peritubular capillaries to pick up the material that is to be reabsorbed from the tubule. Okay? Any questions about this terminology? Because this is how we will speak about reabsorption. So any questions about the cellular anatomy or the terminology? Yes?
Sometimes I'm confused between the word like epithelial and endothelial.
Okay. This is trying to illustrate it. This is an epithelium, and this is an endothelium. Epithelia are much more active. Endothelia are more passive. I'm not saying they don't do things. They release, they're important for constriction and dilation, although smooth muscle does most of that. But what we're going to be talking about now is going to focus on the molecular mechanisms of epithelial transport. Most of the endothelia that we talk about are leaky, and so the paracellular transport mechanism is most important. Okay, so now with that jargon, Bob?
Yeah, when you draw the arrow for transcellular and paracellular, it's like the same arrow, but like what the difference?
Transcellular means a solute is being transported through the apical membrane and then transported through the basolateral membrane into the interstitial space, and that's transcellular transport.
Yes.
Most of what is, so this is then paracellular transport. Is that clear?
Yes.
And we haven't talked about the mechanisms for this yet, but we will in just a minute. We're gonna talk about that right now, for sodium in particular. Did that answer your question, Paul?
Yes.
So whenever you mention paracellular, then it will always be like diffusion?
Yes. Paracellular is diffusion around the cells. Transcellular is going to require some energy. Okay, so here is a complicated slide from not your textbook, from a different textbook. So there's two ways to tell this story. I can tell this story with this cartoon of a nephron, or I can tell this story with words. And you know that I prefer cartoons. So what I would like to do is tell the story with this cartoon of the whole nephron, with this cartoon of epithelial cells surrounding various parts of the nephron. So for example, here is a epithelial cell of the proximal tubule, and here is a epithelial cell of the loop of Henle tubule cell, and here is a epithelial cell of a distal tubule cell, right? So different parts of the nephron do different things, but they're all epithelial cells. And this is the apical membrane, and this is the basolateral membrane. And I'll try to keep, we have to know which side is which, so I'll try to remind you of that. So, and then there will be the words that will summarize, okay? You have the words and you have the cartoons. So let's focus on the cartoons. Here, so the overall story of sodium reabsorption in the kidney, in the nephron. Two-thirds of the sodium that is filtered at the glomerulus is reabsorbed in the proximal tube by active transport mechanisms. If sodium is going to be reabsorbed, that solute is being reabsorbed. Water is going to follow the solute osmotically because the epithelium is leaky. So when the sodium is transported transcellularly by active transport, water is going to follow passively through osmosis because the epithelium is leaky. If the epithelium were tight, water would not be able to follow, but that's not what we got. Okay, a leaky epithelium means if salt moves, and sodium is a salt, there's counterions that we're not going to focus on. Sodium chloride or sodium phosphate or whatever it is, sodium is reabsorbed, a leaky epithelium, water is going to follow. So 67% of the sodium is going to be reabsorbed in the proximal tubule, means a large proportion of the water that was filtered is also going to be, and probably close to 67%, is also going to be reabsorbed in the proximal tubule, because they're going to go together. Sodium being pumped, water following osmotically. Leaky epithelium. In the ascending, so let's do the ascending limb of the loop of Henle. TAL. Thick ascending limb. It doesn't matter that it's thick. It's the ascending limb of the loop of Henle. Sodium is going to get reabsorbed. In fact, about 25% of the total sodium that was filtered is going to get reabsorbed by the thick ascending limb, by the ascending limb. And it's a tight epithelium, so water is not going to follow. You're going to see why that's important in just a minute. I mean, no, probably in about a week. Okay? Then in the, so 60, what is 67 plus 25? 92. 92% of the sodium has now been reabsorbed. By the time we get to the distal tubule, 92% of the sodium has been reabsorbed, but the distal tubule contributes about 5% of the sodium reabsorption, reclamation, and the collecting tubule, both the cortical and the medullary collecting tubule contribute to sodium reabsorption until what is excreted in urine is only about 0.5% of what was filtered. We reabsorb 99.5% of our sodium, of the sodium that was filtered. Zoe?
So 5% is reabsorbed in what part in the?
5% is reabsorbed in the distal tubule,
Okay.
and 3% is reabsorbed in the collecting tubules, both cortical and medullary. And so if you add these up, 67 plus 25 plus 5 plus 3 is 100%. You'd say, well, that's accounting for 100% of the sodium. Well, there's round off error. 0.5%, maybe a little less, is actually excreted.
So
Yeah.
the 5% has errors pointing from different parts?
Yeah, we're not
Or
going to get
just
into
gonna,
that
like,
detail. We
say
are not
that
going to
it's
focus
distal?
on that detail.
The distal tubule?
In fact, well, yeah, I do want you to know, it's important for telling the story of sodium reabsorption to be able to tell me that 2/3 of it is reabsorbed in the proximal tubule, 1/4 of it is reabsorbed in the loop of Henle, and 8% of it is absorbed in the rest of the tubule, the distal and the collecting tubule. I guess I don't care for that you memorize these numbers, but I do want you to have these numbers in your head. Okay, so just 2 numbers for sodium. Well, there'll be more.
So in the previous class,
Previous
around,
class?
yeah, especially the previous class, in the loop handling, there is a
Yeah.
tag around it, and
Yeah.
you told us that the rate absorption of water
Yes.
happens and
Yes, that's right.
and there.
So here we are not, so remember, you have to remember that around these tubules are the peritubular capillaries, and around these tubules are the vasorecta capillaries. There's capillaries everywhere here that are taking in what the tubules give them. Let's not talk about water yet. Water is next week.
Is that the different height as epithelium?
Yeah, so the cells of the ascending limb, the epithelial cells of the ascending limb
Oh, it's
are
about
not permeable to water. The epithelial cells of the proximal tubule are permeable to water. Okay, so we're gonna see this. So now, let's walk, this is a monster slide, but this is the molecular mechanism. These are the molecular mechanisms for sodium reabsorption. So let's take a break so you can come at this fresh. Go get energized, go run around the corner a little bit, because this is important. We are gonna talk about the molecular mechanisms of sodium reabsorption. So let's go through the molecular details of sodium reabsorption. Start here. Okay, I printed this out big for you so you can mark it up, because we are going to cross out the things you don't need to know, and because there's quite a few of them. So I'm trying to be helpful and highlight the things that you do need to know. Okay, so you should mark up your copy the way I'm going to mark up this copy. This is the proximal tubule. This is the lumen, and this is the interstitial space. Just getting oriented. There's capillary over here. Right? So remember, there's capillary here, and this is the urinary fluid over here. What membrane is this? The apical membrane. And what membrane is this? The basolateral membrane. Just getting oriented. Apical facing the urinary fluid, basolateral facing the interstitial space, basically in contact with or closely contacting capillary, not shown. What is that? You already know what that is.
Sodium, potassium.
The sodium potassium ATPase. Nothing in this whole story, nothing for the next 2 weeks is going to make sense unless you remember that the sodium potassium ATPase is working on the basolateral membrane of all of these cells. Sodium potassium ATPase is highly expressed and is running as fast as it can on the basolateral membrane of all of these cells, but let's focus on the proximal tubule, pumping sodium in that direction. There is sodium. We don't have to worry about the 3, but there is sodium being pumped out of the cytoplasm and into the interstitial space where it could be picked up by a capillary. So, pretty simple so far. Okay? As long as we're focusing on the basolateral membrane, let's remember another protein. What would we call this protein? It's got a very helpful name. The sodium bicarbonate co-transporter. Let's not worry about carbonic anhydrase yet. We will on Thursday need carbonic anhydrase, but not today. All we need to know is that there is a sodium pump and a sodium bicarbonate co-transporter that are going to move sodium from cytoplasm to the interstitial space. How did the sodium get in here from the urine, from the urinary fluid? Well, we have a sodium glucose co-transporter on the apical membrane. So now we're focusing on the apical membrane. And we have a sodium proton exchanger. crossed anything out yet, and you say, well, wait a second, you said you were gonna cross some stuff out.
What was the glucose sodium one called?
The sodium glucose co-transporter is moving sodium and glucose. We're gonna need this in just a few minutes. The sodium glucose co-transporter is moving sodium and glucose from urinary fluid into the cytoplasm, and then the sodium potassium ATPase is pumping the sodium out. A sodium proton exchanger is moving sodium into the cytoplasm in exchange for a proton. And then the sodium is going to be pumped out, either by the ATPase or by the co-transporter, the sodium bicarbonate co-transporter. So you can see we have a pathway for moving sodium from urinary fluid through the apical membrane, through the basolateral membrane, into the interstitial space where it can be picked up by a capillary. Let's cross out some things. I'm not going to worry about that. We're not going to worry about that. We do want to know, because remember it's a leaky epithelium, the leak is that water is moving paracellularly through the leaky junctions between the epithelial cells. So when sodium is pumped transcellularly, it's being pumped transcellularly, water is following paracellularly in the proximal tubule. That's the story of 2/3. You now have the story for 2/3 of the sodium and water reabsorption. Okay, but that's 2/3 is only barely passing, so let's go on. Ascending limb of the loop of Henle. So we moved from the proximal tubule, we've skipped the descending limb, and now we're in the ascending limb. You'll see why next week, why we skipped the descending limb. Again, it's a epithelium. We have the urinary fluid, the tubular fluid, the interstitial space, apical membrane, basolateral membrane. Same orientation. We've got the sodium potassium ATPase. Don't forget about it anywhere. We've got the sodium proton exchanger, the same one that we saw there in the basolateral membrane. So that's a commonality between the ascending limb and the proximal tubule. We also have another transporter with a very helpful name called the sodium potassium 2-chloride co-transporter. Sodium potassium 2-chloride co-transporter. So, again, sodium is being pumped from cytoplasm into the interstitial space where it's picked up by a capillary. And that sodium in the cytoplasm is being supplied from the urinary fluid by a sodium-potassium, remember sodium is moving in, and sodium is moving in, by a sodium-potassium 2-chloride co-transporter and by a sodium proton exchanger. What are we not going to focus on now? We're not going to focus on this yet because this is bicarbonate and chloride, so this is not key for us. We're not going to focus on carbonic anhydrase. This little red arrow, this cross sign, means that water is not permeable. Water, just cross water out, because water does not flow here, and water does not flow paracellularly. And we're not going to worry about sodium paracellular diffusion either. This is a tight epithelium. Water does not flow transcellularly, and water does not flow paracellularly. That's different from the proximal tubule. Okay, so now we've recovered 92% of the sodium. So we're in pretty good shape. But we're not satisfied with an A minus. We want to get all the way to an A, right? So let's go to the distal tubule. Apical membrane, basolateral membrane, tubular fluid, interstitial fluid, sodium, potassium, ATP. You can see I'm going faster because the stories are starting to sound the same. Sodium, potassium, ATPase, a sodium chloride co-transporter. It's not the same as the sodium potassium 2 chloride co-transporter. It's a different co-transporter called the sodium chloride co-transporter. But the principle is the same. Sodium is being pumped and sodium is being supplied for transcellular movement of sodium, pumping of sodium. And finally, in the collecting tubule, and this is true in the cortical as well as the medullary, so you can, cortical and medullary, collecting tubule, let's not worry about the fact that it's a principal cell. Sodium, potassium, ATPase, again, pumping sodium out. Now, we have sodium flowing, not by a co-transporter, but by a channel. This is an ion channel. It's got a name, which is going to be helpful. It's called the epithelial sodium channel, ENaC for short. This is the epithelial, it's not the only channel, but this is the one that is most important. Epithelial sodium channel. You'll need to know for your homework an interesting bit that goes on right here. So I'm going to jump to potassium for a minute because this is going to be helpful for your homework. There are potassium channels in the apical membrane of the collecting tubule that work, they are different, they work with the sodium channel. So every time a sodium is imported, a potassium is exported. It's like an exchanger, but it's not an exchanger. It's just two channels that are functioning together in an exchange-ish mechanism. Okay? You'll need to know this for one of the problems on your homework. And so now we have reabsorbed 99.5% of the sodium. Okay? Are there questions? I'm going to have to race. Think of your questions while I clean this up. If I didn't circle it, I forgot to cross it out. So the circles are the most important things. But I tried to cross out the things to help you identify what you should focus on by circling the things that are important and crossing out the things that I don't want you to focus on. If I didn't circle it, consider it crossed out. Okay, so let's move on. Here are the words. This is exactly the same information in words, not in cartoons. So I'm going to skip it because I don't like working with words. I like working with cartoons. But it's all there. Let's skip this. Well, this is just the main point that sodium is pumped transmembrane, and then it diffuses. It is pumped transcellularly, and then diffuses passively into the capillaries. active transport across the tubular epithelium and passive transport across the capillary endothelium. Okay, let's do some clickers. Got a bunch of clickers. Let's do the first one. Which of the following transporters, when I say transporters, I'm talking about a transport protein, which of the following transporters is working in favor of sodium reabsorption in the proximal tubule? Which of these are important to help sodium reabsorption? Those of you who are showing me your answers are mostly showing correct answers because it's all of the above. Let's go find them in the cartoon. Sodium ATPase, sodium proton exchange, sodium bicarbonate cotransport, sodium glucose cotransport. So let's find them in the cartoon. Sodium ATPase, sodium bicarbonate cotransport, sodium glucose cotransport, sodium proton exchange. They're all there. And they're all working in favor of sodium reabsorption. Okay, good. Which of the following best describes paracellular transport of water in the proximal tubule? Okay, so this is an unfair question because I kind of crossed out some information that is correct. So let me just show me your answers. I'll give you a hint. There are two correct answers, one of which is fair and one of which is unfair. Okay, good. Everybody. Oh, well, D is also partially true, but I didn't ask you to know that because I didn't want to give you an unfair question. Okay. Let's do the next one. Which of the following are true? We're talking about sodium. Now we're talking about sort of overall sodium. A and B. The clearance of sodium is less than the GFR because so much of it is reabsorbed. And sodium is freely filtered, and it is reabsorbed. It's not secreted, and it's not secreted. So C and D are not correct, but A and B are. Okay. Questions about sodium? You're going to work with this knowledge with the problem set. We'll be doing histology and talking about tubules in lab. So we're going to reinforce this. I know I'm going through a lot of material very fast, but you'll reinforce this. So let's talk about glucose. Glucose is easy. Glucose is super easy compared to sodium. 98% of the glucose that is filtered is reabsorbed in the proximal tubule. And in fact, that's all we're going to focus on. So we might as well round 98% up to 100%. Let's just say all of the glucose that is filtered at the glomerulus out of your blood plasma is reabsorbed in the proximal tubule. 98% is the correct number, but 100% is an okay number. What are the mechanisms? Okay. What's this? The sodium potassium ATPase, which is pumping sodium out of the cytoplasm. You know that, we just used that. In the previous, when we were talking about sodium transport, we talked about a sodium glucose co-transporter. Before we were focusing on sodium, now we are using the sodium gradient. We are using the sodium gradient to pump glucose. I don't care if you know whether it's 2 or 1. It's the what is SGLT? Sodium glucose transporter. SGLT stands for the sodium glucose transporter. I don't care that you know about SGLT1 or SGLT2. I don't care. I want you to know that it's a sodium glucose co-transporter, and that the sodium gradient is being used to pump glucose into the cytoplasm, but we're not there yet. Then we use a GLUT. What is this? Is this a sodium glucose co-transporter? No. This is just a glucose uniporter. A facilitated diffusion transporter in the basolateral membrane to move the glucose from the cytoplasm into the... So I'm going to use a different color for glucose because I'm using orange now for sodium. Orange is sodium. Green is glucose. Glucose is being pumped using the sodium gradient into the cell and then is going down its concentration passively through the basolateral membrane where it would be interstitial fluid, capillary, picking up, returning the glucose that you filtered back to your blood because you don't want to filter it away. You want to recover 100% of it. Don't care about this content. I want you to know what's on that part of the slide. Yes.
Do we know like the relative concentration of glucose in endothelial cell, in the tubule, and also in the interstitial space? Which one has like the highest concentration?
The highest concentration of glucose is, well, depends on where we are. So no, we don't know. But typically, the concentration of glucose inside the cell is high because it was pumped here, and then it has to flow down its concentration gradient to the interstitial space. So this only works if the concentration of glucose is high inside the cytoplasm. This works regardless of the concentration of glucose because it's being pumped by the sodium gradient, and the sodium gradient was established by the sodium potassium ATPase. So this works regardless of the concentration gradient. This only works if this concentration is higher than this concentration. Okay, so that's glucose. So we'll pick up on Thursday. So there's the words that describe it. But we don't need to go through the words because we went through the images. But it's there for you to refer to if you like words. And we'll talk about diabetes at the beginning of class on Thursday. And then we'll move into bicarbonate and potassium. Okay, good. Lots of progress, lots of material. You have what you need to do to answer most of the questions on the problem set already.